Good morning, everyone. So great to be back here again. Thanks for the introduction, Tim. So I'm going to try and save the planet, well, with your help. Provocative title, but I'm going to try and start off at the high level and then draw it down to some practical issues and some examples of the things that are happening in our sector, particularly the one I'm closest to in the life science sector. So, why do we want to save energy or carbon? What's the direction of travel? Where is energy consumed in the life sciences sector, in our facilities? Then I want to go on to some available guidance and standards. Then talk about some of the opportunities and solutions, so clean room, contamination control related, and then some of the regulatory concerns and risks. So maybe if we're pushing some traditional boundaries, this might induce nervousness from regulators, inspectors, business-to-business auditors. And then at the end, I just want to finish off and remember and make sure we don't forget the clean utilities and the black stuff, the black utilities, because these are huge energy consumers in our business, and of course lots of them drive our clean room systems. I'm thinking particularly of heating and cooling utilities. So let's start off. Direction of travel. Why do we want to get there? Well, I guess the net zero picture is predicated on this sort of emotional stuff that we're seeing every day of the week. I mean, I don't know, the rain was pretty heavy last night, the roads flooded again, presumably the sewage systems, our Victorian systems, will be overcome again today. Floods, and then forest fires and so on. So we're getting extremes, and I guess that's the visual bit. Energy. So certainly around energy consumption, we have been, I think, seduced by years of relatively cheap energy. Some countries cheaper than others. The Ukraine crisis really focused our attention, particularly our dependence on gas, and gas is a major component of our electrical generation still. And I'll mention that challenge ahead of us, particularly here in the UK and most of Western Europe. So, green policies. So, many nations have declared climate emergency, and they have net zero targets, 2035, 2045, 2050, in a period now of diluting some of these, because it's not easy, and we have to invest money to get there. How do we reach this goal? Well, it's clearly important to reduce energy consumption, stop burning stuff. Ultimately, we need to do that. So low or zero carbon grid electricity from renewables and maybe nuclear power. Maybe some applications of geothermal energy sources to reduce fossil fuel burning, particularly for heating and cooling systems. And I'll give you a little case study towards the end. And then the dream, I guess, that we're still looking for carbon capture. Articles I've read recently suggest we're not going to get there without some mechanisms of mopping up CO2 from processes that we cannot do without. So we know this shift comes at a cost, and actually if you're looking at short-term returns on investment, these will generally not be available. And if you're looking at 2 or 3 year returns, you might get some low-hanging fruit, but a lot of them are much longer term. And it isn't human nature to put on a hair shirt, turn off the air conditioner, and drop our living standards. Very difficult to ask ourselves to do that, and I would suggest it's not right or appropriate to say, well, let's get the Chinese to turn off their air conditioners to make a bigger contribution. So the direction of travel is clear. Getting there, I think, is a pathway that is a bit more difficult. So here in the UK, our net zero targets are predicated on a low carbon grid supply of electricity. And this came from early May on a sunny day. I don't know whether you look at this in the morning to see where the grid power is being generated. So typical UK early summer day, 25% renewables, solar and wind, 20% low carbon, nuclear and biomass. Big issue and debate around biomass and whether it's truly a net zero. So all this timber we're getting in from Canada, we mince it up into wood chip and put it into the Drax power station, and it's net zero because the carbon is embodied as a renewable. So that's a slight query there. Now, on this day, 20% of our power here in the UK was imported from France, Belgium, Netherlands, and Norway. The French stuff was mostly nuclear, and the other ones are wind and hydro. So our imports generally are low or zero carbon imports, but 20% imported. So that's interesting on that particular day. So if you want a bit of fun, you can look this up every morning and during the day and see what's happening. But UK and most nations are predicated on moving their grid to low or net zero carbon. 35%, the balance, was burning stuff in combined cycle gas. So this is gas turbines with heat recovery, most of them. And some of those are getting really old. And we're going to have to spend money on replacing those for peak load lopping, so systems that can be turned on and off very quickly. Okay, so that's sort of setting the scene. But we need to understand in our life science facilities where energy is consumed. So we need to start with some evaluation. So we might do instrumentation of existing assets. So to find out where the energy is being consumed in an existing factory. And often factories are very poorly instrumented. You can't really get a good picture of where the energy is being consumed. But electrical power is relatively easy. Heating and cooling energy is a bit more difficult because you've got to put heat meters onto flow and return circuits for heating and cooling systems. You could look at energy bills, a bit of a crude measure, sort of reverse engineer, get hold of the design calculations and find out what the original intentions were to review the systems, their energy consumptions, and look at what they're actually doing. And there's a huge number of building services installations that are 15 or 20 years old and they are out of tune. So they're running inefficiently, or the technology, water chillers, for example, has moved on a huge amount in 20 years. Yet often firms are not writing off and replacing that equipment. Make sure you really understand in a clean room context how that system is working. Is it over-engineered? Where are you operating? Where's your operating norm compared to the GMP regulatory limits? There might be some headroom. There might be something you can do about retuning systems and still remain compliant. And then you want to share and use the information you've got and make management decisions. So, power consumption, fan power, moving air around is a major consumer, heating energy, cooling energy, and I would say quite a strong focus on air volumes, air velocities in unidirectional airflow systems, and so on. I'll come back to that. A really good way of sharing is when you've got all this data, is to use a Sankey type diagram. You've got your inputs on the left, and you can see where all that energy is going. It can help the management process of deciding where the opportunities are. Now, the really hard bit is dealing with, let's say, the gas that we're burning to produce steam, for example. So if I've got a process-driven manufacturing operation that uses steam in sterilization or manufacturing processes, and the steam is also used maybe for deriving my heating services and so on, dealing with that is the tricky bit. How am I going to reduce that consumption? The easy bit is the power used in air compressors, HVAC systems, and so on. So assuming the grid goes green, net zero, then that will deal with that problem. We can still look at efficiency, reducing the consumption, which we should look at as well, of those systems. But remember I said that our net zero journey is predicated on the grid going green. So if we look at that in the context of clean rooms, HVAC systems, so 50 to 80% of the energy in a typical fill finish or biotech facility is consumed by the whole environmental control system. So it's the air moving side and largely the chilling, because the heating is probably derived from a fossil fuel source. So that starts to give us an idea of some of the opportunities that we can go for. So that gives us a sense of why particularly clean rooms, contamination control are high energy consumers, and there may be some opportunities. So let's now look at what is available in terms of standards and guidance that we could use to help us on that journey. So available standards and guidance. So I'm going to start off right at a high level. Now, I find most people have never heard of this, but there is an Energy Management System Standard, ISO 50001 from 2018, and it's a bit like an ISO 9001 or a 14001. It's a management system. There are no energy-related techniques, but it's about the management of the organization following style of ISO 9001, 14001, and so on. Your firm could be accredited to that standard, okay? But it does not include techniques or magic solutions. It's much more a framework for integrating it into the management practices of the business. It includes recommendations, not the techniques for doing it, that you benchmark certain aspects of your operation compared to industry peers, and you document and report energy intensity and improvements that you're making. And you look at that in the context of greenhouse gases, so principally CO2. So that's the essence of that standard. It talks about, in a very generic sense, energy management best practices and management behaviors. And by that I mean it says the firm has to make a commitment. There has to be responsibility designated in the business for worrying about these aspects. And there has to be a commitment to evaluating the potential, prioritizing and implementing energy efficient technologies and techniques. So that would be both for existing assets, so retrospective improvement, and of course for new investments. And it also includes an element that you could link to your supply chain, so materials you're procuring, goods and materials and services, you could have a demand on your supply chain for those suppliers to comply with various aspects. And it's a basis for continuous improvement. And there's a little diagram in the standard, which if you're familiar with quality management systems, you'll see that there's a classic sort of virtuous circle of plan, do, act, and then check and monitor the output from your actions. Okay. So, energy management practice and management system, but no magic solutions. So let's now look at some more standards that have some specific guidance that can help us. So in the ISO Cleanroom standard family, so EN ISO 14644 Part 16, energy efficiency in clean rooms and separative devices, was written in 2019, and for the British people it was derived from a UK standard, a British standard from 2013. And that standard was then converted to an EN ISO standard. And the BSI committee, LBI 30, which I chaired, which Stephen Ward now chairs, was responsible for that British standard. So we're quite proud of that effort. It can be applied, and it was written, so it could be applied to new and existing installations, so clean room installations, and it is clean room related. I'll come back to some details in it. Then we have ISO 14644 Part 4, Design, Construction and Startup of Clean Rooms, and that has in it some elements of both opportunity and good design practice. So a logical design sequence is included in that, from the user requirements right through to the commissioning and startup. And if you were in the life science sector, you would be able to mesh into that qualification and validation practices as well. But it includes some interesting concepts. So for example, avoid unconscious over-design. So everyone adds 10%. Your air handling unit supplier, and the calculations, you make an allowance for the unknowns. You may well find the system is over-engineered. So one of the aspects it considers and suggests is that if you have overage, an allowance for unknowns in your design, it's openly declared rather than hidden, and you design the system so as you get performance knowledge, maybe 6 or 12 months into operations, you can tune the system down. You can reduce the airflow to that which is necessary rather than that which you guessed. And my years of a designer, I promise you, if my client held me to liquidated and ascertained damages for time and performance of the clean room, I was never going to shave the design down to the bare bones. There would always be some overage in the design. So that's a suggestion. ISPE has a sustainable practice working group, and there is an ISPE good practice guide related to HVAC systems in the life science sector. And in that, it identifies lots of good practice, which is energy related. And then, of course, most developed country national building codes have an element of sustainability in those that require us to do some reporting on sustainable aspects of our design. So let's look a little bit more detail into Part 16. Now, in the time available today, I'm not going to drill right down into it. I just want to give you an idea of some of the things. If you are involved in existing assets and wanting to improve them or new designs, this should be sitting in your library of important documents. So first thing, there is a decision tree. Again, I'm not going to try and get you to read this. I really just want to explain the principle. And this helps you work through a logical sequence that you can apply in a new build situation or a retrofit energy reduction program. And it leads you through some basic logical steps. So existing clean rooms, and I've just paraphrased it. So identify systems and departments for assessment. Collate the information on the operational and energy performance of the system and identify opportunities. And select those opportunities and then implement it. Now, all the projects I've been involved in have generally started with the lowest grade, the least demanding facilities and rooms and departments, and then maybe later on move into the more complex, more sensitive aseptic processing facilities. But it's really important to think through before you jump in and start disrupting existing systems. New build, then clearly we start off with user requirements, go through the design in its logical sections and undertake an energy performance design review. So from a GMP point of view, we have to do a design qualification. There should be design quality control built into the designer process, but we should also now add in a dimension there of looking critically at the energy consumption. Have we chosen fans that are efficient? Have we got an optimum airflow? Have we exceeded the airflow for known reasons? We're uncertain about how much clean air we need, so we make an allowance. Is that declared? And then, in an energy-saving project, identify the reduction opportunities, select and implement, and always monitor the performance. So Part 16 has those elements in it. Now, specifically looking at airflow, because airflow in a clean room influences a huge amount of the energy consumption, and that air has to be cooled and heated as well, so it's fan power as well as the other aspects of energy consumption. So it says look very carefully at your fresh air and make-up air supply. So it might be you've specified a very leaky clean room and you're grabbing in much more fresh air than you really need to pressurize the space, and you will pay for that. Focuses on source strength of contamination in the room. So moving away from some magic 20 air changes per hour and targeting the amount of clean air in non-unidirectional airflow rooms to meet the dilution of the contamination that's generated. And then ventilation effectiveness, so how that clean air effectively ventilates and dilutes the contamination, becomes really important. And remember, Annex 1 of our GMP talks about recovery time of clean rooms. It doesn't mention anywhere any magic minimum air changes. So airflow rate estimation is included in Part 16, so it gives you some guidance on the information you need to gather. I promise you this is the most difficult bit. So if you decide you want to find out how much the machine is generating, you'll find very few vendors have got this data. There are other ISO standards, suitability standards for equipment in clean rooms that vendors could use to characterize the contamination source strength of their equipment. There is some published data about particle contamination emitted from people, so we can use that as well as a source strength contribution in our calculations. It suggests air velocity reduction in unidirectional airflow rooms, either permanent or silent hour reduction. So it's interesting, in many of our life science operations, the clean room spends most of its life asleep, unoccupied, at rest. We don't need to blast the same volume of air in as we do when it's in operation. So power management, turn down, turn off, really important. And then the final one there, active control. I mentioned that a little bit more in a minute. There are some clean rooms now in service, quite recently been brought into service, that use variable air volume systems. I'll come back to that. Heating and cooling loads, so be critical of those. It may be possible to remove some cooling loads at source rather than they become a room load. Fan and filter selection for low energy, and then think about the operation and maintenance of the system. So effective maintenance, keeping the system tuned, will maintain the original design intent, energy consumption. Part 16 has a whole lot of informative annexes, and I'm not going to go through those. You can look at those in your own time, but it includes lots of, I call it soft guidance. They're not absolute requirements. You won't find engineering solutions. You'll find prompts for things that you should consider in your existing facility energy saving project or in your new build. And it includes things like specific fan power and other benchmarks of energy efficient components. Okay, part 4, design, construction and startup. So part 4, has a flow diagram in it, which goes through the sequence. I mentioned that earlier, and you could mesh into this qualification and process validation if you needed to. So logical sequence. There are comments in there that say avoid hidden over design, design review at all stages, and it links to part 16, and it says design in features to allow tuning and regulation once feedback from performance is known. This is tuning out that overage that you might have included in the design. So let's look at some of the opportunities. ISPE's HVAC Good Practice Guide, and I've just put one example up here, indicates in a large system the benefit of having separate outside air pre-treatment feeding into multiple departmental air handling units. That would generally give you a more efficient system than having your outside air load dealt with in a single recirculatory system. So outside air pre-treatment can be important, particularly in high humidity environments. Choosing the optimum contamination control solution. So this slide really just focuses, actually isolators may have the opportunity of significantly reducing the most expensive grade B cleanroom space. So you will be able to manufacture with your surrounding environment at a lesser grade, and that will consume less energy because the cleanliness levels are less. Supply air volume based on need, not a magic 20 air changes per hour. So be aware of ventilation effectiveness, how I deliver the air into the clean room and use that clean air most effectively is important. Low pressure drop designs, so low frictional loss, so efficient fans and motors, and low resistance system components, filters, coils, duct sizing. So they can all be sized for minimum size, which tends to give you a larger pressure drop, or you can increase the size and reduce the pressure drop, which reduces the power consumption. Operational controls, silent hour setback, velocity and volume. Velocity in unidirectional airflow, volume in non-unidirectional airflow. And then something that's now being actively used in some new applications, active demand control. So variable air volume clean room systems based on measurement of temperature, maybe relative humidity, and airborne cleanliness in the space. So instead of at a fixed volume, you vary the supply air volume. So VAV-based systems, so there's an example, and Eco2, who are here today, have a number of examples, and there's one that they published data on. So it's a multivariate measurement of air cleanliness and associated temperature in the clean room space to proportionally control a variable air volume system. And it's linked to outside air and the room pressure control system. So that's important. And the critical quality cleanliness attributes in the facility are monitored by a separate environmental monitoring system. Important to think about clean room testing. So as we start to shave the design nearer to the edge of failure in a way, we're reducing air volumes, we need to make sure that we have commissioned and tested the facility to a really good standard. So key ones I would take, test methods from part 3, the ISO testing standard, are things to do with air volume and velocity testing, recovery testing, this is giving you your measure of ventilation efficiency, and something we've already heard about today on one occasion, which is airflow visualization. So we can see here airflow hoods, and we can see flow grids, so I might install those in ducts. A lot of detail around airflow hoods and uncertainty and error of measurement. They can be highly disrupted by air diffusing systems, and we need to be very clear how our measurements with anemometers, are they giving us true information about the air volumes or velocities in the system. And airflow visualization is a critical part of our qualification. And I found, and you'll see this firm Vosentech outside, who have developed a convenient airflow visualization device, which is fantastic for detective work. And it's interesting, we've got another talk from Morgan Poland on airflow visualization this afternoon, and concepts are out in the exhibition, and we heard from La Vision about their Schlieren photography approach. So clearly airflow visualization is a big and important topic. We mustn't forget our processes. I mean, this is a clean room related conference, so I'm going to go through this very quickly. Single-use systems in biotech, huge numbers of single-use systems. It's all plastic. Get spaghetti junction like this. The advocates of the technology claim that it's lower cost and more flexible than fixed systems, stainless steel and glass. Avoids cleaning and sterilizing in place, so that's a big energy saver. Most of the surveys I've read say that the energy reduction outweighs the environmental impact. I'm not sure. The issues, leachates and material compatibility. Lots of GMP stuff about that, which has been generally well documented and dealt with by vendors. But there's nervousness around recycling and a suggestion that maybe some of these, particularly composite plastics, that are impossible to recycle. And maybe 20% of the components are recyclable. End of use. ISPE did a really interesting survey of the industry. What do firms do? 36% of the respondents incinerate the waste. 25% incinerate with heat recovery. 27% landfill it. And 12% do something else, undeclared. So what should we do with this stuff? You know, end-of-life plastics are actually really only valuable as a fuel. So I would suggest they have to go into, ultimately, incineration with waste heat recovery and probably carbon capture, which means you've got to collect all this stuff together and put it into a centralized industrial plant and use the energy that's trapped in these materials that cannot be recycled. They're often contaminated as well. Okay, regulatory issues. Some thoughts about the risk. GMP says we can use all sorts of alternative approaches provided we meet the intent of the GMP. So this could apply to air volumes, air flows, and so on. Reliability and repeatable performance is a fundamental. So we've got to be careful that our energy efficient systems don't become unstable and unreliable. GMP does not contain any green component. The Finnish regulators actually said that the European documentation should include in GMPs a sustainability component, but they were, that was pushed out. So the intent is important. So the GMP has a very clear intent about performance, not how to get there. So what are some of the regulatory concerns? So I see very often, if you decide you're going to have less than 20 air changes per hour in unidirectional airflow, some regulators say, no, impossible, it must be 20. So you might have to deal with that battle. And similarly, if you have lower unidirectional airflow velocities than the magic 0.45 meters a second, that's sometimes a red rag. The other area is that reducing air volumes and having active control makes the HVAC system more complex. And more complexity means you've got to be more careful in your design, and maybe there are more components and more maintenance and so on. So just to finish off, lots of opportunities, but don't forget the utilities. So clean and pure steam. So we need high temperature steam for many of our processes. But we have options. Water for injection, we can move from distillation to membrane technology. Vapor compression distillation could also be used. The black utilities play an important part as well. Chilled water systems, I said at the beginning, legacy systems are often inefficient. We can have much more efficient modern chillers, recover condenser water heat, two-port variable volume chilled water systems, lower condenser water temperatures, improves coefficient of performance and recovered heat. So, chilled water systems, buffer tanks to reduce peak demands and flatten the curve can end up with more efficient chillers. And we need anyway to change our refrigerants in a lot of systems to the low global warming potential. Final example, and we'll finish here, geothermal for primary utilities. This comes from Janssen in Belgium. I'm quite proud of this because my son runs an engineering business in Germany that engineered the geothermal system for this. They drill down nearly 2,500 meters for heat. Right? This is oil well drilling with directional drilling. And they're getting water out at 85 centigrade. There's a 2.5 kilometer heat network that runs around the site. Some of that water is used directly to substitute burning fossil fuel. They already use green power from the North Sea wind to power the site. There was quite a bit of financial support for this investment. And it's linked now to high temperature heat pumps, which are available from firms like Siemens, so I can now get an industrial heat pump that can elevate from 85 to 150 degrees, which is nearly enough for sterilization. So I could generate steam from that if I needed that for a sterilization process. So there's an awful lot happening. Final thoughts. We don't have all the answers. The solutions are moving on. The standards and guidance give us a lot of help. Identify the opportunities, think outside the box, and push the boundaries of convention. Good quality design and construction becomes even more important. And accurate and well-documented commissioning. Thank you, Tim. I think I've run over a fraction.
Yeah, that's all right.
But you made me start late, so that's...
Gordon's left absolutely no time whatsoever for questions, but Gordon is not leaving today, so Gordon will be around for the duration of today and tomorrow. Thought-provoking, as always, and I think very important in the climate we're in globally, not just nationally, for power. So really interesting conversation, Gordon, discussion. Let's give Gordon a round of applause.
Thank you.
Well done. Very good.